All right, so we're going to continue with our unit in electrochemistry. Today's lesson is covering galvanic cells. So what we learned in our previous lesson, we learned that in electrochemistry, we're oftentimes dealing with the spontaneous transfer of electrons that takes place between two substances. And many of these reactions, called redox reactions, take place spontaneously. And so we can harvest this energy from this electron transfer and possibly store it. And in this lesson, excuse me, you will learn how this energy can be harvested through special cells called galvanic cells and some of the practical applications of these galvanic cells. So recall from our previous lesson that the reaction between zinc metal and copper ions. And in this reaction, our zinc atom loses electrons to become oxidized, and our copper ions gains these electrons to become reduced to copper atom. So if you recall, that Leo the lion, so Leo, loss of electrons is oxidation, and gain of electrons is reduction. So if you remember that, you're in good shape. So if you lose electrons, you're becoming oxidized. If you're gaining electrons, you are becoming reduced. So then we can take this oxidation reduction reaction here, and we can simplify it into half reactions. And in a half reaction, we show that either—
Sorry, I'm late.
Hi, Borna. Yeah, no problem. Thanks for joining in. We have just started our lesson. You have not missed much. We were just talking about this reaction between zinc metal, copper ions, becoming copper atom and zinc ions, and just reviewing that this is a redox reaction. And we know that loss of electrons is oxidation, gain of electrons is reduction, and we can use our acronym of Leo, the lion goes GER. L-E-O, Leo goes GER, G-E-R. So here we can see that our zinc atom is becoming oxidized to zinc ion, and it's losing electrons. It's ending up with a positive charge, so it's lost electrons as a result. And this loss of electrons is oxidation. And the reverse has happened for our copper ion. It has gained electrons to then become neutral, to go from a +2 charge. It has gained electrons now to become neutral, to be copper atom. So we can take this full redox reaction and write it up as half reactions. And half reactions show either the reactant that is oxidized or the reactant that is reduced. So two half reactions are needed to completely represent a complete redox reaction. So one shows oxidation, the other one shows reduction. And here I have the two half reactions split up from this redox reaction. And we have the zinc ion becoming oxidized, the zinc atom becoming oxidized to zinc ion +2 electrons. And here we have the copper ion gaining 2 electrons, so +2 electrons becomes the copper atom, and this is the reduction. So in the half reactions, first of all, the atoms and the charges have to balance. And second of all, the coefficients must be in the smallest whole number ratios. Okay, so we wouldn't want this to be, 2 copper ions +4 electrons becomes 2 copper atoms, because that is not the smallest whole number ratio. The smallest whole number ratio would be 1 copper ion +2 electrons goes to one copper atom. And then you have to make sure that the atoms are balanced. So if you have one zinc on this side, you have one zinc on that side. If you have two of something, then you have to have two of that element on the other side as well. The same goes with both sides, and the same goes with the electrons. The charges must be balanced too. So if you have a neutral on this side of your reaction, on the reactant side, on the product side, the charges have to add up to be neutral as well. So that if you have 2 plus charges, you have 2 electrons, 2 negative charges. 2 positive plus 2 negative balances out to be 1 neutral. So this is the charge is balanced here in this half reaction. The same with down here. Here you can see the charge is also balanced. Here our copper atom is neutral. It doesn't have any charge. It has 0 charge. So the copper ion, which has 2 plus 2 charge, will be balanced by the 2 negative charges of the electron, of the 2 electrons. And this side, the charge will add up to be 0, the same as this side. So this side is equal to that side for both oxidation and reduction half reactions. Okay, so now let's talk about the galvanic cell. Here in a galvanic cell, we have a device that spontaneously converts the chemical energy into electrical energy. And in this galvanic cell, and the setup is shown here, we have electrons flowing from one reactant to the other through an external circuit. So here I'm showing the direction of the flow of the electrons from zinc to the copper. Okay, and then you have a porous barrier, or what's called a salt bridge. This is called a salt bridge that separates the two half cells. And this salt bridge is often filled with some kind of an electrolyte solution that will allow the passing through of a common ion in between. And the oxidation half reaction occurs in one of the cells, and the reduction half reaction occurs in the other cell. And each of these half cells is filled with an aqueous solution, and the reactants have to be separate in order to retain their full electric potential and to get this spontaneous reaction. For this reason, we know that the galvanic cell is made up of 2 beakers, and each with its own electrolyte solution. So in this case, the electrolyte solution is a zinc sulfate, and in this case, it is a copper sulfate. And then these conductors, these immersed conductors, they carry the electrons into and out of the connected wires, and these ends are called the electrodes. And the electrodes are given then 2 names, 2 special names. One is called the anode, and one is called the cathode. At the anode, the electrons are released by oxidation reaction. So here the electrons are released by the oxidation reaction. This is the anode. And at the cathode, the electrons are used in a reduction reaction. The electrons are flowing this way, they're coming in, and they're being used in the reduction reaction. And here's the reduction reaction written up. And just a memory tip, because I know I myself and probably many, many people, and so hence this memory tip, it's hard to remember what is the cathode and what is the anode, which side is called the cathode, which side is called the anode. So they use this memory tip of anode and ox. So if you can picture this ox and ox, that's where the oxidation reaction occurs. And then for the cathode, if you remember red cat, so an ox, red cat, that might help you remember that the red cat reduction happens at the cathode, oxidation happens at the anode. An ox and a red cat. That might help you. So then actually, there's a clip on YouTube that I found that just illustrates this galvanic cell very nicely, very pictorially. I really liked it. I would share that with you. I'm sure there's lots of YouTube videos that you can watch on galvanic cells to really help you visualize and understand these reactions and the flow of electrons between the anode and the cathode. So let's look at it together, and we'll come back and we'll pick up where we left off. Okay.
In this video, we're going to talk about galvanic cells, which are also called voltaic cells.
So can everybody see that? Did I share that properly?
Yes.
Yes, perfect. Okay.
So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation reduction reaction. But we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab. So here's what they are. First, we start with two beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution. And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solutions. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2+ ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here, we have these Cu2+ ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper here, okay? So we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with wire, it kind of starts a tug of war between the zinc and the copper. They're having a tug of war for the electrons. One of them wins and one of them loses. It turns out that Cu2+, these atoms here, Cu2+ has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons. So in this tug of war, Cu2+ ends up winning. Let me show you how this happens. So Cu2+ really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away 2 of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change. It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2+. Now, changing from neutral zinc to zinc 2+ has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom turns into Zn2+, because it lost these electrons, it's no longer part of the solid metal anymore, and it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then over here, these electrons make their way down the wire to the copper, and one of these Cu2+ ions, which really wants electrons, is going to come over here, and these 2 electrons are going to be added to the Cu2+ ion. Gaining these 2 electrons is going to get rid of that 2+ charge that was on the copper. And that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now, notice that for this whole process to happen, electrons have to move through this wire, and that's where the electricity, the electron movement comes from. Let's see that one more time. So zinc loses 2 of its electrons here. Those move through the wire. Loss of those 2 electrons causes zinc to take on a 2+ charge. It is then going to dissolve in the solution. These 2 electrons are going to move over here to copper. And one of these Cu2+ ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2+. It's going to get rid of the 2+ charge. And this neutral copper atom is now going to become part of this solid piece of copper metal. So that is where this electron movement through the wire is coming from. Zinc loses these 2 electrons. They move through the wire, creating electricity. They come over here and they join up with a Cu2+, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if this happens long enough, we actually see these two pieces of metal change, right? Like these zinc atoms keep coming off of this piece of zinc. So it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2 plus ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these two pieces of metal actually change size and shape. Here's some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2 plus ion is gaining 2 electrons to turn into a neutral copper atom. So reduction or gain of electrons is happening over here. Now, we can give names to these two parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. So the piece of zinc is going to be the anode. So reduction at the cathode on copper, oxidation at the anode on zinc. Now, let's write reactions for the two processes that are happening, okay? First, let's write the reaction for reduction. We're starting with Cu2+, and this Cu2+ is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2+ gains 2 electrons, so I'll write plus 2E-, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral, and then it's part of the solid metal, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom, and this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow, okay? So I'm not going to write anything right here. I'm going to put this arrow, I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2+ ion, Zn2+, that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2E- on this side. So this is the reaction for the oxidation. Now, these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process. And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place. And it is these half reactions that show what's going on in each one of the half shell, in each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway, we have these two half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process. We start with solid neutral zinc and Cu2 plus ion, and then at the end of the process, we're left with zinc 2 plus ion, and then we have solid copper. This is the net ionic equation that we get from adding together these two half reactions. Now, when we're talking about voltaic cells, we're often asked to represent them in cell notation, which is a shorthand abbreviation of the chemical reactions in the voltaic cell. It's a way that we can show what's going on without drawing a picture of the whole thing, okay? Cell notation is sometimes referred to as a cell diagram, just so you know. So here's how we would write what's going on in this voltaic cell using cell notation. We start on the left with the oxidation process, okay? How does the oxidation process start? Well, I have the half reaction up here. It starts with solid zinc, okay? So I will write Zn solid right here. That's how the oxidation begins. Then I put this line here, and I show what we end up with in the oxidation process, which is Zn2 plus, okay? So Zn2 plus, and that is dissolved in water. It's part of the solution. It's aqueous. So this shows the oxidation process that happens in the half cell over here, okay? Then I put two lines like this, and these two lines represent the physical boundary between these two half cells, or you can think of them representing the salt bridge. Okay, now on the right, I put information about the reduction process. So the reduction process begins with Cu2 plus aqueous, Cu2 plus aqueous, and then I will put another one of these lines, and the reduction process ends with Cu solid. So there's Cu solid. So this is how we can sum up what's going on in this voltaic cell using cell notation. We have the oxidation process, and then two lines showing the boundary, and then we have the reduction process. So finally, we've talked a little bit about the salt bridge. I said we discuss it at the very end. So let me take a minute or two and explain what the salt bridge is, what it does, and why it's important in a voltaic cell. The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean. The two solutions are made up of both positive ions and negative ions. I didn't show the negative ions before. Those are these yellow things. I just showed the zinc and the copper. But along with these metal ions are these polyatomic ions, sulfate, SO4 2-. It's a sulfur with 4 oxygens, and the whole thing has a 2- charge. I didn't want to have to keep using this thing, so I've just abbreviated these as SO4 2-. But the point is, the negative charge from the sulfate balances out the positive charge from the zinc or from the copper. So right here in my two half cells, the charges are balanced out. But let's look at what happens as the voltaic cell begins to run for a while. Okay? Over here, these zinc atoms are going to give electrons to copper. So they are going to end up with a charge. I'm not showing the electrons here, but electrons are getting sent up here as these turn into Zn2 plus ions and as they enter the solution. Now over here, as electrons come over, these Cu2 plus ions will turn into neutrally charged copper atoms and attach to the metal. And now look at what's happened to the charge, okay? Now we have all of these Zn2 pluses, but we have only a few of the SO4 2-. So after just a little while, positive charge really begins to build up in this half cell. And then over here, as the positively charged ions like this lose their charge by gaining electrons and turn into neutrally charged copper. Now, there are a whole lot more SO4 2 minuses than there are Cu2 pluses. So a negative charge begins to build up on this side. And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that in our case is filled with sodium chloride. You can see the Na plus and the Cl minus ions. Now at the ends of the salt bridge, there are cotton plugs, a little bit of cotton there. And the cotton prevents the solution from just pouring out into the half cells. But these ions are able to slowly pass through the cotton plugs, and here's what happens. We said that negative charge is going to start building up in the half cell over here. And so the positively charged Na plus, is going to begin moving over into this half cell to help balance out the charge. So the Na plus ions are going to begin moving in this direction to balance out the negative charge. And over here, we said that positive charge begins to build up. The Cl minus ions are going to begin moving through the salt bridge to come out through the cotton and help to balance out the positive charge that builds up on this side of the voltaic cell. So over time, what we're going to see is we're going to see that the Cl minuses move in this direction to balance out the positive charge that builds up here. And then we'll see that the Na pluses begin to move to this side to balance out the negative charge that builds up here. A salt bridge helps to balance these charges to make sure that they don't build up too much, and that would prevent the voltaic cell from being able to work. Wow, so we just learned so much about galvanic or voltaic cells. Okay, so here's the basic structure of a voltaic cell. We have the zinc sulfate solution here, copper sulfate solution here. We have zinc metal and copper metal. Now, when we hook this all together, electrons start flowing from the zinc to the copper. And that's because copper that's in the solution has a strong pull for electrons, whereas the zinc has a weaker pull, so the copper wins. As electrons move from the zinc to the copper, they are lost in the zinc, so oxidation takes place, and they're gained here in the copper, so reduction takes place over here. We call this the oxidation half cell, and we call this the reduction half cell, because oxidation is happening over here. The piece of zinc is the anode, because reduction is happening over here. The piece of copper is the cathode. Then finally, we can write half reactions for the two processes that are happening in the different half cells. Here is solid zinc losing 2 electrons because they're moving out to turn into a zinc 2+ ion, which is going to enter the solution. And then over here, Cu2+ ion that's in the solution gains 2 electrons and turns into solid copper. It's going to attach to this metal right here. And then finally, we can sum all of this up by writing this cell diagram or cell notation, which shows everything that's happening in a shorthand abbreviated form. Zn solid, then a line, Zn2+ aqueous. This shows the oxidation part. Then we have these 2 lines representing the salt bridge or the boundary between these 2 cells. And then we have the reduction part, Cu2+ line giving us Cu solid. So that is how a device like a galvanic or voltaic cell uses a chemical reaction to create electricity.
Right.
Let's talk about the chemical process of electrolysis. I wanted to try to write the simplest definition that I could. So here's what I came up with.
All right, so yeah, I thought that video kind of nicely showed in great detail, actually, exactly what is happening here.
Sorry, Miss. Will we get the link of the video, because I got caught up, I don't know why, a couple of times, so I missed just like a little bit of the video.
Okay, yeah, so I have the link of the video down here.
Thank you.
And yeah, you guys can use it to go and find it. Yeah, this actually that guy, I think his name is Tyler DeWitt. He does a lot of these kinds of videos where he just uses very simple paper cutouts to illustrate things, and I just find it's I like it. So you can maybe even search and find more of his videos that might be useful to you in illustrating certain concepts in chemistry. He does a pretty good job of explaining things in great detail, and by doing it in a visually interesting way. So yeah, we talked about this galvanic cell. The other name for it is the voltaic cell. And in the video, actually, he covered this shorthand notation, because you don't want to, every time that you're talking about a voltaic cell or a galvanic cell, to have to draw this detailed picture with beakers and electrodes and wires and all of that. So there is a shorthand way come up for illustrating the details of a galvanic cell. And so this is exactly what he was showing in the video. This is exactly how it's written up. And we always start with the anode on the left side. And remember, anode and ox. The anode is where the oxidation reaction is happening. And the cathode is always shown on the right side. And cathode, if you remember red cat, that's where the reduction is happening. And so you begin by writing the half reaction, the oxidation reaction that's happening at the anode, exactly as it is. A zinc, solid zinc atom is becoming oxidized to give zinc ions, which are aqueous. And it's very important that we write the solid and the aqueous here. And those two that are part of that same reaction are separated by a single straight line, vertical line. And then on the right side, separated by a double vertical line is our reaction that's happening at the cathode, our reduction reaction. And exactly the half reaction that's happening at the cathode is that we have copper ions that are aqueous in solution, becoming reduced to solid copper atoms. And that is the shorthand notation or cell notation, a shorthand way of representing the reactions of a particular galvanic cell or particular voltaic cell. So for example, if you've got given this redox reaction and you're asked to write the oxidation and reduction half reactions, and then you're asked to show this reaction in shorthand notation. So the first step we want to do is to assign oxidation numbers that we learned how to do in our previous class to determine the oxidation and reduction reactions. So here, nickel atom has got an oxidation number of 0. Copper, it's an ion, a single ion on its own, so it has a charge of +2, so the oxidation number for it is also +2. Here, nickel ion has got an ionic charge of +2, so the oxidation number for this ion is also +2. And then solid copper is got an oxidation number of 0. So here we can clearly see that nickel is oxidized because its oxidation number increases. It goes from 0 to 2. And we can see that copper is reduced. Its oxidation goes down from +2 to 0. So we write down the half reactions of nickel goes to nickel ions plus 2 electrons. And we know it's 2 electrons because nickel has got a charge of +2. And we need to make sure that the charge is balanced on both sides of the reaction. And so in order to end up with a neutral charge, to have 0 charge here on this side, we need to have 0 charge on this side, and we get that 0 charge by putting in 2 negatively charged electrons, and those will cancel out the 2 positive charges on the nickel ion. And we write the same thing, same idea for copper, but copper is reduced. So we have the copper ion, aqueous, in solution with a +2 charge, and it is going to copper atom with no charge. And so in order to do that, we need to add 2 electrons to it because it's becoming also reduced. And when things get reduced, they gain electrons. And these 2 negative electrons will then cancel out this 2 positive charges on the copper ion, and you will have a neutral copper atom. So now we've written out the oxidation half reaction, we've written out the reduction half reaction. They are balanced. We have the same number of nickel on this side and that side. We have the same charge that's balanced. On this side, it's an overall charge of 0. Excuse me, on this side, we have an overall charge of 0 as well. Then in part B, we're asked to show this reaction in shorthand notation. So in shorthand notation, we always start by writing the oxidation reaction, which happens at the anode on the left side, and the reduction reaction, which happens at the cathode on the right-hand side. And we write it exactly as we have it. Nickel atom, solid nickel atom, goes to, so a single vertical line goes to nickel +2 in the aqueous. I'm just going to fix this since I'm here right now. Oops. Okay, good. So yeah, nickel is oxidized to nickel ion. And on the other side, and the other half cell, we separated by 2 vertical lines. And on the other half cell, we have copper ion reduced to copper atoms separated by a single line. So that is the shorthand notation for that oxidation reduction reaction for this complete net ionic equation. Any questions up to this point so far? I think things are probably pretty clear, but if you have any questions, please go ahead and ask me. Okay, so we're going to move on to standard cells and cell potential. So cell potential is the measure of the electric potential difference, or the voltage, between 2 half cells. And the standard international unit, the SI unit, is the volt. The symbol for it is the symbol V for volts. And it's defined as 1 joule of energy per coulomb of electric charge, or 1 volt is equal to 1 joule per coulomb. And coulomb, as you might know, is the SI unit for electric charge. So 1 coulomb is defined as 6.25 times 10 to the 18 electrons. Now, cell potential depends on a few things. It depends on the design of the cell. It depends on the redox reactions that are involved. And it also depends on the concentration of the reactants. A standard cell is referred to as a galvanic cell in which each of the half cells contain all the components shown in a half cell reaction at standard temperature and pressure. So SATP stands for standard temperature and pressure, with a concentration of 1 mole per liter for the aqueous solution. For example, the shorthand notation for the standard zinc and copper cell is written like so. This is the standard zinc and copper cell notation. And underneath it, you write 1 mole per liter for the aqueous solution. So if you notice, the 1 mole per liter is written underneath the aqueous components, right? So the standard cell potential, which is written as delta E naught R of the cell, this is the electric potential difference, and it's a difference. So therefore, there's this delta sign here. This is referred to the electric potential difference of a cell that's operating under standard conditions. And standard conditions or standard temperature and pressure and 1 mole per liter. And it's a measure of the potential energy difference per unit of charge between the anode and the cathode. So what's the difference of the potential energy difference between the two sides? So each half reaction is then written as a reduction, and it's called the reduction potential. So even though it's an oxidation half reaction, you rewrite it as a reduction, and these are called reduction potentials. The standard reduction potential, this E naught R, represents the ability of a standard half cell to attract electrons and undergo reduction. And as the cell operates, each half cell, or the half cell with the greatest reduction potential, the one that's more positive, gains electrons from the half cell with the lower reduction potential. So then the delta ER of the cell is defined as the delta ER of the cathode, not the delta, so the ER, the standard reduction potential of the cathode, minus the standard reduction potential of the anode. So what do we mean by that? Let's look at this table in the next page. So this table that is also, I've taken from a table in appendix B7 of your textbook. You can find this exact table there as well. This lists the standard reduction potentials of many half cells measured relative to the standard hydrogen half cell. So here is a setup of, here is the hydrogen half cell, and in the hydrogen half cell, the electrode is often platinum, and there's hydrogen gas that's in that space. So, and then different metals are connected on this side, and the potential difference is the standard reduction potential difference is measured across. And you can find it here. For example, here is copper, and you can see this device is reading 0.34 volts. And on the table, if you find copper, copper is 0.34 volts. That's a standard reduction potential of copper. So all of these metals are measured with respect to this hydrogen half cell. And so there's a list of them here, starting with the strongest oxidizing agent, which is the weakest reducing agent here at the top of the list. And as you go down towards the bottom of the list, you have the weaker oxidizing agents. So for example, you can see here, and here is that hydrogen at 0. So that is the two sides, the stronger oxidizing agents and the weaker oxidizing agents. And here we can see that copper is a stronger oxidizing agent than zinc. Okay. So that's why in the zinc and copper reaction, you have the zinc becoming oxidized by the copper, and the copper is becoming reduced. Yeah. Sorry, did I miss anything else here? Okay, so the other thing that I guess I should point out is that in this standard galvanic cell, these half reactions for the hydrogen at the anode is written like this. You have the hydrogen gas, it goes to hydrogen, it becomes oxidized to hydrogen, to 2 hydrogens with a single plus charge on them, so an overall charge of +2, and of course +2 electrons to balance out those 2 positive charges here. And if you notice, it's 2 hydrogens because on this side we have 2 hydrogens. H2 gas is a molecule of H2 gas, has got 2 hydrogen atoms on it. And the same for what's happening here at the cathode. In this example, what's at the cathode is copper, but it could be any of these other metals here. And at the copper, then the oxidation reaction, the reduction reaction is taking place. We have the copper ions becoming reduced by gaining electrons and becoming copper atoms. This is at the cathode. And this has a potential of 0.34. And you can find that on the table. And all the other metals, the potential for them is also listed. So these standard reduction potential tables list the standard reduction potential of many of these half cells. They're measured to that standard hydrogen half cell, which we talked about. The half cell reactions don't happen on their own. So by assigning the standard hydrogen half cell an electric potential of 0 volts, then the electric potential of the other half cells can be determined relative to the standard hydrogen half cell. And the convention is that we always write the equation for these half cell reactions from left to right as reduction reactions. So they're always shown as reduction reactions. So they're always shown as the ion plus electrons going to form the what's finally reduced. So the copper ion is gaining electrons, and gaining of electrons is a reduction reaction. And finally, you have this copper atom at the end. And that's the way they're written for all of the metals and all of the molecules. So that's the convention on standard reduction potential tables. And the reduction potentials can then be used as a predictor of the cell potential for a galvanic cell that involves any pair of these half cell reactions. And so more easily reduced ions or molecules would have higher reduction potentials, whereas poorly reduced ions or molecules would have lower reduction potentials. So for example, these examples that I'm just trying to show, the copper, for example, would have a higher reduction potential, and the nickel. So here you can see, I'm trying to find, so there's copper and nickel, for example, here. So copper is a stronger oxidizing agent, and the nickel is less so. So these values are for these standard conditions, which means that you have a concentration of 1 mole per liter, and the temperature and pressure are standard temperature and pressure. So in other words, 25 degrees Celsius or 298 Kelvin. And the pressure is 101.3 kilopascals or 1 atmosphere. That is standard conditions of temperature and pressure. And then these values are, as I said, relative to the hydrogen electrode, which is assigned a value of 0. So these are all with respect to the hydrogen electrode, which is assigned a value 0. Let's look at an example. I'm sorry, guys. I'm actually quite sick. I'm losing my voice. Okay, so let's look at an example. In this example, we're asked to calculate the standard cell potential here for this reaction shown in cell notation. So here we're shown that at the anode is zinc, at the cathode is copper, and the concentrations are 1 mole per liter. So, and we can do this using two possible ways to solve this problem. And let's look at this method 1 and method 2. So here we can see that we have the copper plus 2 electrons going to, we found the reduction potential from the table. That half reaction that's always shown as a reduction. We found this from the table. So you look it up in the table and you find it there, for example. And these are always written as reduction reactions. And we can find the zinc one there too. And it has a value of negative 7.76. So we write down these reduction half reactions from our table. You note the values of the standard cell potential. And so you can either do it that way and then use the method of, for the cell, it's the value for the cathode minus the cell potential value for the anode. So at the cathode, we have the copper, right? Here we have the copper at the cathode. So we write down its value, 0.342, we write 0.342 volts, minus the standard cell potential for the anode. And at the anode, we have the zinc. So we take the value for the zinc, which is negative 0.762 volts. And if we do the math, we will end up with 1.104 volts. Or you can think of it as the other way. You can take these reactions that you have, and then you can take the one that is happening at your anode, and it's actually an oxidation reaction. But in the table, by convention, if you remember, they're all written as reduction reactions. So then you can rewrite this by turning it around and writing it as its oxidation reaction that it actually is. And that becomes the zinc oxidizing to zinc plus 2 and 2 electrons. And by reversing that reaction and writing it as an oxidation reaction, you also have to change the sign for this for this voltage on the standard cell potential. So it becomes a positive sign. And if you do it using this method, you get the cell potential is the reduction cell potential plus the oxidation one. So you get 0.342 plus 0.762, and it becomes 1.104. So either method is correct. You can do the one that makes most sense to you. But you have to remember that if you're doing it in this way, if you're using this method too, what you're doing is for the oxidized anode, you have to turn the reaction around, you have to flip the sign and then you have to add them up. Whereas in method 1, you just take the values directly as you see them from the table and you subtract the one that is from the cathode minus the one from the anode. So cathode minus anode, and you get your answer. And these standard reduction potential values are values that you can find in the appendices at the end of your unit booklet as well. And you'll always be provided these values and these tables in an exam situation. We'll be giving you these kinds of tables in order for you to look up these values and do the questions, okay? Now, how to calculate a standard cell potential? Let's look at another example. So if you've got a reaction, a redox reaction, it says write the two half reactions for this redox reaction that you have here and add the standard reduction potential and the standard oxidation potential to find the standard cell potential for the reaction. So here you're being told to write the two half reactions. So let's do that first. Step 1 is to write the equation in its ionic form to identify what are the half reactions. So let's break this apart into its ions. So here we have solid sodium plus water, and it goes to sodium hydroxide, which is aqueous. So that means that it can be pulled apart into its ions, plus hydrogen gas. So if we write the equation in its ionic form, we can see that we will have 2 sodium ions in its aqueous form, so dissolved in the solution, plus 2 hydroxide ions in their aqueous form, dissolved in solution. So first we write the oxidation and reduction half reactions. So the oxidation half reaction, which is the one that is occurring at the anode. So remember, oxidation happens at the anode, anox. And this is always accompanied, oxidation reactions are always accompanied by a loss of electrons. So you can see the sodium atom becomes sodium ion and it has lost an electron. There's an electron on the product side of the equation. Then you have the reduction half reaction. You write the reduction half reaction, which occurs at the cathode. So remember, red cat. Reduction happens at the cathode, and reduction is always accompanied by a gain of electrons. So here we have our water molecule is gaining 2 electrons to give 2 hydroxides plus the H2 molecule. Now in the step 2 is we have to look up these reduction potentials from the table. So the standard cell potential for the reaction is equal to the standard cell potential for the reaction happening at the cathode minus the standard cell potential of the reaction happening at the anode. So cathode minus anode. So we look it up. What do we have happening at the cathode? At the cathode, it's this water reaction. So we find this half reaction on the table and boom, there it is. And the value is negative 0.83. We write that down. Minus, so we write down our minus and we look up this value for the standard cell potential for the reaction that's happening at our anode. And what's happening at the anode is this half cell reaction. And on the table, we locate this very reaction right here. And we write down the value for it. Bring over the value, put it into your equation, do the math, and you'll end up with the correct value for the standard cell potential for this reaction. So, but what you have to notice is that You have to make sure when you're writing these half cell reactions that they're balanced. So both the number of molecules and the number of elements are balanced, so that if here we have 4 hydrogens and 2 oxygens, we see on this side of the equation, we also have 2 hydrogens here and 2 hydrogens there, which will add up to 4. And we have 2 oxygens here. And then the 2 hydroxide ions will have an overall charge of 2 minus. So we have a charge of -2 on this side of our reaction. So we have to make sure we have 2 electrons on this side to make sure we have 2 minus charges and 2 minus charges on either side of the reaction. Now for this one, because sodium was neutral and sodium ion has got a single plus charge, we would want to put down a single electron to make sure it neutralizes that single positive charge to balance and be the same as what we have on this side of the reaction, which is 0, which is neutral. All right, there's a couple of support questions for you guys to practice with. And then let's take a look at dry cells and batteries. So we were looking up to now at wet galvanic cells. So these wet galvanic cells, they harvest electric energy, but it's a very inconvenient way of transporting them around with you, carrying them around with you, this wet bucket of solution sloshing around. A more convenient way of carrying around these cells with you would be to make them into a dry cell or a battery, which is what we use typically on a daily basis. A battery is where you have 2 or more galvanic cells connected in series. There are, as you know, many types of batteries, cylindrical or rectangular. There's large ones, there are small ones. And although they are very widely in the composition and their form and what's actually constituents in the battery, they all work basically on the same principle. And a dry cell battery is essentially comprised of a metal electrode or a graphite rod. It's this thing in the middle, surrounded by a moistened electrolyte paste that's enclosed in a metal cylinder. So here is that cylinder, and inside is this wet paste. So all of these cells have 3 basic parts. They have an anode, they have a cathode, and they have an electrolyte. And in the diagram, the anode is zinc. Here's the zinc, the anode. And the cathode is a mixture of the manganese dioxide and the carbon. And then you have a very thin porous fabric that keeps the anode and the cathode chemicals separate while allowing electrons to still go through. So that was kind of the idea of what the salt bridge was doing for us in the wet galvanic cells. And in this case here, the half reactions are what's happening at the cathode is that you have this manganese dioxide plus water plus electrons gaining electrons to give this manganese. I have to say, I don't know how to say the name of that chemical, this MnO2H plus 2 hydroxide ions. And the zinc reaction is happening at the anode. So the zinc plus 2 hydroxide ions is what's happening is the oxidation reaction, and it becomes zinc oxide plus H2O plus 2 electrons. And then the other important things to take from this slide is that a primary cell is a cell that cannot be recharged, while a secondary cell is a rechargeable cell. So Those are just two terminologies for you guys to know. And then there's a couple of support questions to practice with. And then what ties here is corrosion. Corrosion is the spontaneous redox reaction of substances in their environment. So corrosion most often happens with metals that come into contact with oxygen from the atmosphere. So if you have a bicycle or anything metal sitting outside for a long period of time, you'll find that parts of it may start to rust as the metal reacts with the oxygen in the air. For example, iron railings or iron fences, things that may have iron, quickly oxidize when reacting with the oxygen in the atmosphere and form rust or iron oxide. And also you see copper oxide, which is that green color that you see when copper starts to rust. Sometimes you have copper roofs and they start to rust, and you have that beautiful green patina of copper oxide. There's the reaction for that. But what is needed is if all of this was, if all these metals and oxygen were kept in a perfectly dry condition, this oxidation won't happen, this rusting won't happen. Water is needed for rusting to occur. And the carbon dioxide in the air then dissolves in the water to form a very weak solution of carbonic acid. This is carbon dioxide and water mixed together, carbonic acid. And carbonic acid is a weak acid that turns water into an electrolyte. So the redox chemistry of rust is that a corroding metal is actually very much like a galvanic cell, where you have parts of the metal is the anode, and another part of that same metal then is the cathode. And let's look at the corrosion of metal iron as an example. So at the anode, you would have your solid iron before it gets all rusty. And when it does start to rust, it becomes iron +2 ions +2 electrons. Now at the cathode, you would have oxygen and water gaining 2 electrons, becoming reduced to give hydroxide ions. And then there are several factors that affect the rate of corrosion, as you know, such as the amount of moisture. The more moisture that there is, you'll have more corrosion. And if you have dissolved electrolytes, if for example, where there's salt, you get dissolved electrolytes, that tends to accelerate corrosion. If you have contact with a less reactive metal, that tends to, again, produce conditions that is very much like a galvanic cell and affect the rate of this corrosion. And in places where you have mechanical stress, so if you have a piece of metal and it's been bent, for example, at the spot where it's bent or pinched, where there's been mechanical stress, those are oftentimes the spot where rust and corrosion will start to take hold. So then finally, there's the key questions, which we have, it's not due actually, these key questions are not due this Sunday. They are due the following Sunday, Sunday, November 14th. So this Sunday, the key questions for 13 and 14, key questions 13 and 14 are due this Sunday. Key questions 15 and 16 are due the following Sunday on November 14th. Okay, guys, that brings us to the end of our lesson here. And here is a complete standard reduction potential tables at the end that you can use when you're doing your practice questions, and just remember that all of these are written in half reactions, and by convention, they are written as reduction reactions. So you can see in all of them, these are all written as reduction reactions. And you have to make sure that sometimes when you're using this for your questions or for writing up, drawing out galvanic cells, you might have to flip some of these reactions around. All right. Is there any questions? All right. So if there's no more questions, I think I am going to end today's class a little bit early. So you guys can always contact me by email to ask any questions. Again, as always, I have shared this lesson with you in your Google Drive. And yeah, I think that's it for tonight. If nobody has any questions, I'll say good night to everybody.
Bye, Miss. Thank you.
Have a great night.
Thank you. Have a
Bye.
great night.
Thank you, you too.
Goodbye.